So, where things are at. On Monday, you need to submit your draft submission of the reservoir sizing calculations. And the only thing you need to provide for that is an Excel file. So, don't make it a screenshot of an Excel file. Don't make it a PDF of the Excel file, you know, the actual Excel file. And if you missed the demo that we did in class back on the 15th, that video is posted on YouTube and you can review the process. I went through an example of what calculations you need to perform in order to do the reservoir sizing. So then the next thing in line after that, homework 11, I've just posted that to Blackboard. It's some problems related to hydraulic jumps. You probably could get started on it after today's class. There are problems from the textbook, but I've provided some extra hints in the PDF that's describing the assignment. So that'll be due on the 5th, and then on Monday the 8th, we're going to have class online because I'm sure some of you are already aware that they're having an eclipse that day. I guess maybe that's the wrong way to put it. It's not that they're having an eclipse, it's that an eclipse is happening. So I'm planning to go up into the zone of totality. I don't know. I saw the eclipse back in 2017 and I thought it was pretty interesting. So, you know, maybe you should consider it as well. It's relatively close. If you drive up to Canton or Columbus or over towards Cincinnati, you can get into where the eclipse is going to be. So I'll put a lecture online for that Monday class meeting, but we won't meet together face to face. Yeah.
You got an extra seat?
Yes. Yes, I do. You'll have to have the dog on your lap, though. You don't mind?
I'm assuming it's a smaller dog.
It's a medium-sized dog.
I'm used to
Big ones? Well, we're golden. Yeah. All right. Yeah, my parents live about 45 minutes south of the zone of totality, so it'll be easy for me to stay with them over the weekend and go north up to watch the full eclipse. But you should definitely get as close as you can because it's interesting to, suddenly it gets dark in the middle of the day. All right, so today we're going to move on to some ideas in chapter 13. We're talking about rapidly varying flow. Any other questions before we move into hydraulic jumps? So let's just review where we're at with open channel flow. When conditions are steady and uniform, like they were on the exam with that first problem, what it means is that you can calculate the normal depth according to Manning's equation. So the normal depth, just what makes it normal, that would be the flow conditions if nothing is disturbing it. If there's no changes in slope, changes in geometric characteristics of the channel, if it's just steady and uniform, then the depth is determined by Manning's equation. If we have variations like a contraction of the channel or an expansion, if the channel bed goes up or down, then we can use specific energy analysis to find the new depth. And we can also use specific energy analysis to find out what would be the new depth after choking. If there's some obstruction that exceeds the maximum tolerable obstruction and it forces choking upstream, then you can use specific energy analysis for that as well. Where we're moving on to now is looking at what happens when there's a transition between upstream there was supercritical flow and then downstream there was subcritical flow. To have the flow starting off as supercritical, and so here in this first section what you can see is that the slope is steeper than the critical slope. And the critical slope is defined as what is the slope that would cause critical depth. So if you had a slope steeper than that, then it's going to force supercritical flow. And that's not the only thing that will cause supercritical flow, but it's one thing that would. So if you had a steep slope join a mild slope being one that's less than the critical slope, then that forces a hydraulic jump. And so what we need is some tools to describe what will be the new depth downstream after it goes through that transition. And the reason why we need new tools is that energy is not conserved in the same way as it is with a channel expansion, contraction. And even when energy isn't conserved, remember the way that we handled it was by having some coefficient on the right-hand side of the equation, a C value that was similar to a local loss, and we just accounted for the energy loss as a function of the velocity head. But that won't work with a hydraulic jump. Energy isn't conserved, but momentum is conserved. And so we can use that approach to find out what's the new depth downstream. So by momentum, you may remember back in fluid mechanics, momentum is in a closed conduit environment looking at what forces would need to be applied to a flange in order to hold a valve steady. You know, like if we had a contracting diameter and then a jet of water coming out, you've probably felt that before with a hose. You know, if you're spraying off a car at home and you've got a really high velocity coming out of the hose, you kind of have to push back against the natural motion of the valve to hold it steady. And so the momentum equation says that there's some external force required to hold the system steady if there's a difference in velocities. So it's a change in velocities. Here we had a large diameter, meaning a slow velocity, a small diameter, meaning a fast velocity, and it was the change in velocities and also taking into account the pressure effect in this enclosed section of the pipe, that the difference between those two is why an external force has to be applied to hold the system steady. In open channel flow, the situation's a little bit different. If we have, for example, water flowing downstream and some change in depth, then the momentum equation in a case like that has two terms. It has a hydrostatic term, which is related to the depth to the centroid. So here h bar, what I'm talking about is the depth to the centroid. From the surface downward, how deep is it to the center of area of the cross section? So this is the hydrostatic component of momentum, and this is the dynamic component of momentum. So if we have q squared divided by g a1, this is just a function of how quickly the water's moving. So both of those play a component in the total amount of momentum in the system. And so if we just looked at a certain location upstream and a certain location downstream, we could use this to find out how the momentum is changing from maybe predominantly dynamic in the case of a shallow depth to predominantly hydrostatic in the case of an increasing depth. So if you multiply both sides of this equation by the unit weight of water, gamma, then the units end up being units of force. If we did kind of an analysis of the units, area multiplied by depth gives you volume. Multiply that by unit weight, now you've got newtons. So units of force on both sides of the equation. So this momentum analysis is useful to us in trying to determine what the new depth may be after a hydraulic jump. So let's look at some of the things that could cause a hydraulic jump. We already saw this one. This one was where you had a steep slope joining a mild slope, and so the steep slope was causing supercritical flow. The mild slope can't support supercritical flow. So there's no reason for the water to be flowing supercritical on a mild slope. It may temporarily, but not for long. Eventually it will have to jump up to a subcritical depth, and it will go through a transition that's the hydraulic jump. So this is one kind of real world scenario that would cause a hydraulic jump, and you see this when you're river rafting sometime. If there's a steep section of rapids and then it flattens out to a more shallow part of the river, it's very often that there would be a standing wave in the river in a location like that where you've got steep slope joining mild slope. Here's another case of some sort of a physical interference with the flow that could cause a hydraulic jump. This is a mild slope, so ordinarily we wouldn't expect to see supercritical flow on a mild slope, except that this gate is causing pooling upstream. So we put a gate down into the water, and that forced the water to rise upstream of the gate until there was enough energy to force the water under the gate at a high velocity. So this high velocity flow under the gate is supercritical, but it's supercritical on a mild slope, so it can't be sustained indefinitely. And so what it does is it'll gradually increase for a little bit, but then it goes through a hydraulic jump, which is a rapid variation in flow, and it matches the downstream depth that can be supported on a mild slope. Here is what would happen if we had a steep slope and a gate. It's kind of a really weird case where instead of the hydraulic jump being downstream of the gate, the hydraulic jump is actually upstream of the gate, because what's happening by the gate being where it is, it causes pooling, but the water gets deeper than it ordinarily would be on a steep slope. So we have supercritical flow that jumps up to subcritical flow, then the water goes under the gate, supercritical, and it stays supercritical, and it only goes through a gradual transition until it reaches its equilibrium depth that's consistent with this steep slope. Finally, another place where we often see supercritical flow leading to a hydraulic jump is flow over a spillway. And so if water's flowing over the top of a dam, it gains a lot of velocity as the water's flowing down the face of that dam. It's moving very quickly, but then it reaches a shallow slope again. So this is really a variation of the first case, because the first case is saying steep slope meets shallow slope. This is the same thing. Steep slope meets shallow slope, but the steep slope itself wasn't just the channel, but it was a hydraulic structure, meaning the spillway of a dam. So you can see it's supercritical where it shouldn't be, where it can't be supported because the slope is mild. Eventually it will gradually increase for a little while, but then it will go through a hydraulic jump. So what we'll do later is we'll talk about, how long will it go through this gradual variation, and then when does it pop up into the hydraulic jump. So like this little shaded area is meant to imply we'll see some pictures of and videos of hydraulic jump today, but it's like a foamy rolling water where depending on the Froude number in the hydraulic jump, you can actually visually with your eyes see the rapid transition and increase in depth. Okay, who remembers a diagram that looked like this? What did we call that diagram earlier in the semester? Specific energy diagram, good. So specific energy diagram. And on the horizontal axis it had units of energy, and on the vertical axis it had units of depth. So specific energy diagram, when did we use those? What was it related to? Do you remember when we made specific energy diagrams? Yeah, that's one of the things it tells us is the critical flow depth. But what kind of analysis were we most interested in? For finding alternate depths. Good. So alternate depths are two depths that have the same amount of specific energy. Excuse me. So we used this when we were doing like the step down, step up, contraction, expansion, the specific energy analysis. This is different from a momentum depth diagram. Even though it looks a little bit similar, it's not the same thing. So let's talk about a momentum depth diagram. So the reason why it looks similar is like it's a sideways curve that points towards the vertical axis. It has some minimum point. So like the shape is similar, although it's not exactly the same. Because the specific energy diagram, it almost always flattens out to a line in a way that the momentum depth diagram isn't going to flatten out to a one-to-one line. But, it does share some similar characteristics. But where these were alternate depths, remember, were two different depths that has the same amount of specific energy. A momentum depth diagram, if you go up and cross that curve, then Those are called conjugate depths, or sometimes also known as sequent depths. And what it means is it's two depths that has the same amount of momentum. And this is the key to finding out what is going to be the new depth after a hydraulic jump. There's two main ways to solve it. One is graphically with a momentum depth diagram, and we can also do it numerically with something called the Bellinger momentum equation. And we'll do both ways. We'll analyze hydraulic jumps with the graphical approach and the numerical approach. But this is just basically a graph of the two components of momentum. The hydrostatic component of momentum, which is the cross-sectional area of the channel, multiplied by the depth to the centroid, h bar. And then the dynamic component of momentum, which is related to the flow rate, the gravitational constant, and cross-sectional area. So so another one of the similarities between a momentum depth diagram and a specific energy diagram is this minimum point is associated with the critical depth. So that's a common thing. And then when you're on the underside of the momentum depth diagram, those are all supercritical depths. And when you're on the top side of the momentum depth diagram, those are all subcritical depths. Like if this is critical, any depth less than critical is supercritical depth. Any depth greater than the critical depth is subcritical depth. So some similarities, some differences. We are going to use that template file that I told you about on Blackboard and create both a specific energy diagram and a momentum depth diagram, just so we can compare and contrast the two of those. So this is a channel which has a width, a bottom width of 6.5 meters, and we're putting a flow of 15 cubic meters per second through that channel. And there's a variety of different depths which correspond to the variety of different slopes that we could put in the channel in order to cause those depths. So let's open up that template file and get started working on that together. Excuse me. Okay, so you can see that our channel is 6.5 meters wide. It's rectangular, which is nice because it makes it easy to calculate the critical depth. By the way, problem 1 on the exam, that channel was not rectangular, right? So if you want to calculate the critical depth, you can't use this formula unless it's rectangular. So we're going to use this one because this is a rectangular channel, but you couldn't use this equation to calculate the critical depth of a triangular channel because there's no meaning to flow per unit width if the channel isn't rectangular. So with that said, what we're going to do is we're going to look at for a variety of different depths. You wouldn't necessarily know which depths to use if you were creating a momentum depth diagram from scratch. Sometimes that's an iterative process to try some depths and see how does your graph look and then adjust as needed. But just so for simplicity's sake, I've already specified which depths we need to use. So let's put in the width of the channel, which we know to be 6.5 meters. And that applies to all of the different rows. So every row is for a flow rate of 15 cubic meters per second. And now h bar for a rectangular channel is just half the depth. It's not quite that simple if you've got a trapezoidal channel, but if this is your depth y, then h bar is just half the depth. So y divided by 2 for a rectangular channel. So let's do that. Equals this divided by 2. You're going from the top of the water to the center of area. And the center of area, like if you think about centroids that you learned about, back in statics, the center of area of a rectangle is halfway down from the top. Of course, if it was trapezoidal, then the center of area would be closer to the top. It would be less than halfway because, you know, these sides would bring the overall center area average upward. Okay, so let's apply that formula down through all of the depths, just depth divided by 2. Okay, so the area will be the width multiplied by the depth. So it's this B value multiplied by whatever depth we've got to find the cross-sectional area for that depth. And now if we know the area and we know the flow rate, then we can find V by Q divided by the area. So that's the formula we're going to apply for this column F. It's the flow rate divided by the area. So we've got some really high velocities associated with the small depths. We've got some really low velocities associated with the deep depths, and then a lot of values in between. Now, specific energy is defined as the depth plus the velocity head. So if we're going to do a specific energy diagram, then it's going to be the depth of flow plus V squared divided by 2 divided by G, 9.81. Okay, so we already have everything we need to make a specific energy diagram, because a specific energy diagram has depth on the vertical axis and energy on the horizontal axis. So we've got those two things defined. But the momentum depth diagram, we have to have the momentum function. So it's this formula that we're going to apply to calculate the momentum associated with each depth. So Q squared divided by G, 9.81, divided by A, plus A times H bar. Excuse me. Now you could use the, parentheses. I think I've told you before about my trick of I just divide by multiple times because it ends up being slightly fewer keystrokes than putting in the parentheses. The other way to write this would be, so Q squared divided by, parentheses, 9.81 times A, close parentheses. So that is the same as just saying divided by G, 9.81, divided by A. And it's one less keystroke. Think of all the time that you could save throughout your life with that one extra keystroke. You go on vacation, spend time with your family. All right, so the dynamic term plus the area term. Okay, so we've got the momentum function defined, and we'll apply that same formula down through every row, meaning for all of the different slopes and all the different depths. Okay, so I guess it would be interesting for us to calculate the critical depth just to see, like, if it works out to be the minimum of both the specific energy and the minimum associated with the momentum function. So let's calculate the critical depth here where we're using this formula. So the flow, if this flow rate is 15, then Q, lowercase q, is in terms of meters squared per second. That is the flow rate divided by B. Okay, so this is the flow per unit width. Which only applies for a rectangular channel. Here, 2.308 meters squared per second. And then we'll use that to calculate the critical depth. So it is the flow per unit width squared divided by G, 9.81. and then all of that to the power of 1/3. All right, so the critical depth is 0.816. Now, coincidentally, that happened to be one of the depths I asked you to calculate the specific energy and the momentum for. So, you're like, what we wanted, the whole point of doing that is just to see, is that truly the minimum specific energy? And yeah, it does appear to be the minimum specific energy. And also, it's the minimum momentum function. So here's our critical depth. Now the graph, oh, did I already have it set up to just automatically make the graph? I guess that saves you from having to format and labels and so on, but is yours doing the same thing where it's already got the graph built? Okay. So if we look at that, you see what I mean about the shape? The specific energy diagram, it turns into a flat line in a way that the momentum function, it's not quite the same. It continues curving. But they do share those similar characteristics of they're both pointing over at the critical depth on the vertical axis. And there is two places where you'd cross the curve. If you go straight up from a certain amount of specific energy, those are alternate depths. Can use to find alternate depths for same specific energy. Whereas here, the momentum depth diagram can use to find sequent depths for the same M. So if you have a hydraulic jump, the depth before the jump and the depth after the jump would be two crossings of the curve with a vertical line. So for example, if you have this water flowing, like if we had this channel and we had 15 cubic meters per second going through it, and we measured the depth before the hydraulic jump and it was 0.3 meters, what we do is we'd say, all right, we know we have 12.05 cubic meters of momentum. Where else do we have about 12 cubic meters of momentum? Well, it's like between these 2 points. So we could tell that if our upstream depth was 0.3 meters, then our downstream depth is going to be about 1.75 meters. So if our starting depth was 0.3, we'd go over, intersect, up, and then to the left again, and then that's how we could graphically determine what is going to be the downstream depth after the water experiences the hydraulic jump. So now you've drawn both a momentum depth diagram and also a specific energy diagram. Any questions before we move on from the Excel part? So hydraulic jump is where you have supercritical flow at a location where it cannot be sustained. And why can't it be sustained? Because the slope is mild. And so if you have a mild slope but supercritical flow, it can't continue forever. And it's going to go through this rapid transition to find the new subcritical depth that has the same amount of momentum. So let's watch a little video, a YouTube video that explains a little bit more about hydraulic jumps. Pause my recorder. Downstream. And it's a bad thing to carry sediment downstream because it can be damaging to aquatic life. It can, over time, cause the stream to change its path. You know, like if you've got a lot of scour, then it could make the banks unstable. So it's really important to dissipate that energy. And this video did a good job of explaining how it's an important process of trying to design a location where you force the hydraulic jump to occur in a location where you've got like a concrete lining at the bottom, because if it goes through the hydraulic jump after this stilling basin, then you're having quite a lot of turbulence tearing up the channel, the naturally earthline channel or gravel or whatever the channel's made out of. You don't want the hydraulic jump to occur, in the natural stream, but in a location where you have a little bit more rugged environment that can handle all of the turbulence that's occurring. So, Froude number is an important parameter that's going to go into the Bellinger momentum equation. We have to be calculating the Froude number when we are doing sequent depth calculations, because it's a part of of the equation that we use to find the downstream depth. And remember that this version of the Froude number always applies regardless of what the channel shape is, but then there are certain simplifications that we can use that only apply if it's a rectangular channel. So conjugate depths are the depths that have the same amount of momentum upstream and downstream of a hydraulic jump. We can go through the graphical approach like we did it earlier in today's class. And that process is just that you have some initial critical depth that's known. You'd intersect the momentum curve, find the alternate or the conjugate depth, which is another crossing point with the same amount of momentum, and then you'd go back over to the vertical axis and find out the new downstream depth that's associated with the same amount of momentum. That's the graphical approach. The numerical approach here uses the Bellinger momentum equation, and here you can see that what we're solving for is the unknown downstream depth after the hydraulic jump based on the upstream depth prior to the hydraulic jump, and meaning immediately prior to the hydraulic jump. Because as I mentioned earlier, sometimes there would be a period of gradual flow that precedes the rapid variation in flow. And so let me just draw a sketch on the whiteboard to emphasize that point. So here's the bottom of the channel. And what if we had a gate that was partly open and it caused pooling upstream, and the pooling meant that the water is moving very fast under this because, you know, the deep water has a lot of pressure at the opening, so it's moving at a high velocity, and so it's going to continue to contract for a little bit, and then it may go through a gradual increase before it finally goes through a rapid increase in depth. And so the Bellinger momentum equation is saying Y1 would be immediately before the hydraulic jump. It's not during this section. This is going to be some other depth, but there's a gradual increase in depth before it finally, the reason why it's gradually increasing for a while is that this Y2, the downstream depth, Y2 meaning after the jump, this is the normal depth that's associated with the downstream. And so it's going to go through a gradual increase until the upstream depth is matching the downstream depth. So it's not like the water is thinking, but the water is increasing its depth until the amount of momentum matches the downstream depth that has to be matched up against after the hydraulic jump. So this Bellinger momentum equation, Y1 is before the jump, and Y2 is after the hydraulic jump. And so you can see that one way to determine the downstream depth is as a function of the Froude number upstream. So FR subscript 1 means the Froude number here at location 1 before the hydraulic jump. Or the other way to do it is as a ratio of the critical depth to Y1. But notice, this is the Froude number squared, whereas this is 8 times the ratio of depths to the third power. So just pay special attention to like what's the exponent that you should be using, whether you're going with the Froude number or the ratio of the depths. Now, this equation, it's not perfect. It has some assumptions that aren't true. So, for example, there isn't a uniform velocity distribution. You think about what that means. Uniform velocity distribution is saying this equation assumes that the velocity before the jump is the same at every depth. Well, we know that's not true, ever, because of the no-slip condition. But that's what this formula is assuming. And like, why is it assuming that? Well, because the math would be a lot more complicated if we didn't assume that. So like, this isn't always going to be 100% accurate. Like if you take this formula and you go out into the real world and you do physical observations, it'll be pretty close, but it's not going to be perfect in predicting what's actually happening out in the field. And one of the reasons why it's not going to be perfect is because of the underlying assumptions. One of which, probably the most egregious, being it's assuming a uniform velocity distribution. It's assuming this, where we know more realistically the velocity distribution looks like the water's moving faster at the top than it is at the bottom. So we've got big velocities at the top, slow velocities at the bottom, and then like right in contact with the water surface there's no velocity because of the no slip condition. So another one of the assumptions is it's assuming a hydrostatic pressure distribution, and that's okay. That's not like the worst assumption in the world as far as like interfering with accurate predictions, but the water is moving. It's just saying, like, as you go down through the water, how does the pressure increase? And the hydrostatic equation, which is delta P is delta H times gamma, that really only applies if the water isn't moving. And so here, the pressure distribution is pretty close to the hydrostatic, but not exactly because the water is moving. So another assumption is it's assuming that you've got a horizontal bed, so that it's assuming that the elevation of the channel at 1 and at 2 is the same. And well, that's not going to be true because otherwise water wouldn't be flowing downstream if it was truly horizontal. So what this is saying is that the more steep your channel is, the worse this is going to be at predicting reality. That this works best when you have a relatively horizontal channel, if you've got a low slope. And then the other thing that it's assuming is that boundary shear stress is negligible. So like the side of the channel, if this is rectangular, think into the page. It's also assuming that there's not a velocity distribution. If we're looking down, so this is a top view, it's assuming that the velocity at the side of the channel is the same as the velocity at the middle of the channel. And what do we know would be more realistic? Well, if we've got a concrete sides on it, then the water's going to be slower at the edges. That would be more realistic, is that it's not moving as fast at the edges. But this has no way to account for that. So with an understanding of those limitations and knowing that this equation's never going to be perfect at predicting reality, we can still use it and get pretty good results with it. But in a more sophisticated environment where precision is really important, then there would be other ways of predicting the downstream depth besides just this simple Bellinger momentum approach. Energy loss occurs in a hydraulic jump. Momentum is conserved, but energy is not conserved. And we can estimate how much energy is lost with this formula. And so the units of delta E would be units of length. So it's going to be, for example, meters of energy that's lost. So we'll work on an example when we get together next week on Monday. We'll try out the Bellinger momentum equation, run some calculations, and we'll also calculate delta E just to see how much of the initial energy that existed in the flow is dissipated through a hydraulic jump. And it depends on how intense the hydraulic jump is and the ratio of the depths. If you look at the parameters here, if you have a relatively gradual transition, like if y1 and y2 are not changing much, like if the depth is just going up by a little bit, then you're not going to lose much energy. But the more dramatic the change in depth, then there's more turbulence associated with that, and as a result, there's a greater amount of the energy that's lost. So this is where we're going to leave it for today. Just as a reminder of where things are, we have design project phase 3 on Monday, and then Friday of next week you've got some hydraulic jump calculations due, And then Monday of next week, you're going to go and see an eclipse. At least go outside. I think it'll be noticeable in some minor way, even this far south. But that's it for today. Hope you have a good weekend.